GCE Advanced Level Chemistry Practical Series Experiment number 45, Determination of Dissolved Oxygen in Water by Winkler Method. The aim of this experiment is to determine the level of dissolved oxygen in a water sample using the Winkler method. Dissolved oxygen is an important water quality parameter, students, and it is often abbreviated to DO. And dissolved oxygen refers to the amount of molecular oxygen dissolved in water. This includes atmospheric oxygen and oxygen released from photosynthetic aquatic plants. Oxygen is nonpolar, water is polar. So oxygen is not going to be very soluble in water. However, we have a certain amount of oxygen still dissolved in water, and this supports aquatic life. At sea level, around 21 degrees Celsius and 1 atm pressure, the dissolved oxygen level is going to be 9 parts per million, or in other words, 9 milligrams per liter. If this dissolved oxygen level falls down to 5 milligrams per liter, at that point, aquatic life will experience stress. If it drops down to 1 or 2 parts per million, at that point, fish will start to die. So, as you may have already realized, dissolved oxygen content is a very important water quality parameter. This will tell us whether a water body can support aquatic life or not, especially if the dissolved oxygen content goes down to around 0 parts per million or very close to 0 parts per million. This creates an anaerobic aquatic environment which will not be able to support certain aquatic life. So students, while keeping this in mind, it is now time for us to move on to the next part where we identify the chemicals and the equipment we will be using for this experiment. Now students, let's identify the chemicals and the equipment we'll be using for this experiment. For this experiment, we'll be using potassium iodate, and using this potassium iodate solid, we have prepared a solution of potassium iodate with a concentration of 0.00167. So you can see here we have prepared a solution of potassium iodate with a concentration of 0.00167. We are going to use potassium iodate in the first part of our experiment when we are standardizing the thiosulfate ion solution. And using sodium thiosulfate 5H2O, we have sodium thiosulfate 5H2O. Using sodium thiosulfate 5H2O solid, we have prepared a solution of sodium thiosulfate with roughly a concentration of 0.018 moles per decimeters cube. So this is a rough concentration of sodium thiosulfate solution that we have over here, and we are going to use the potassium iodate and potassium iodide solutions that we have over here to standardize the sodium thiosulfate solution later on in the first part of our experiment. And then we have potassium iodide over here, students, and using potassium iodide solid, we have prepared this potassium iodide solution. So potassium iodide solution is made to a concentration of 4 moles per decimeters cube. So this particular potassium iodide solution was made by dissolving the relevant mass of potassium iodide in 8 moles per decimeters cube concentrated sodium hydroxide solution. So we have prepared 8 moles per decimeters cube concentrated sodium hydroxide solution, and using that solution we dissolved the potassium iodide and prepared a solution of potassium iodide in alkaline medium with a concentration of 4 moles per decimeters cube. So this potassium iodide solution we have over here was prepared by dissolving the relevant mass of potassium iodide in 8 moles per decimeters cube concentrated sodium hydroxide solution. And to prepare this 8 moles per decimeters cube concentrated sodium hydroxide solution, we used sodium hydroxide solid. So this is sodium hydroxide solid, or as you may know, sodium hydroxide pellets. And then using MnCl2, manganese dichloride, or MnCl2 also can be referred to as manganese 2 chloride. So using this MnCl2 solid, we prepared a solution of MnCl2 with a concentration of 3 moles per decimeters cube. Apart from that, we have our starch here. Using our starch in this bottle, we have prepared a starch solution by dissolving our starch in hot water. We have prepared a starch indicator here, or starch solution. Apart from that, we will be using sulfuric acid with a 50% dilution. So we have 50% sulfuric acid. We'll be using distilled water in this experiment, and the main purpose of this experiment is to calculate the dissolved oxygen in a water sample. So in this experiment, we are going to be using well water, and what I have in front of me here is a sample of well water. Then we have graduated pipettes, which we will be using for this experiment. And what you see over here is a pipette filler, students. We'll be using digital balance. So a digital balance would be used when measuring all of these solids when you're preparing their solutions. And then we will be using a burette, measuring cylinders. We'll be using measuring cylinders. Apart from measuring cylinder, students, we'll be using titration flasks to carry out the titrations we see in this experiment. And when you are filling water or when you're collecting water for this experiment, you have to collect water into these amber colored reagent bottles or darker colored reagent bottles. This is much preferred as some of these reactions that are taking place in this particular method is going to be light sensitive. So therefore, we can use these amber colored reagent bottles. However, when you use an amber colored reagent bottle, you will not be able to observe the color changes that are taking place when we are carrying out the reaction. So for your benefit, so that you can observe the color changes that are taking place, we are going to be using a clear reagent bottle to collect our water sample, so that when you're carrying out the reaction in this particular reagent bottle, you will observe the color changes that are taking place. Although a darker or amber color reagent bottle is preferred, when you're using a clear bottle, we can show you what the color changes are going to be when we are carrying out this reaction. So when you are actually conducting this experiment, to obtain a more accurate result, it is preferred if you can use a darker colored reagent bottle. So with that in mind, students, we can now move on to the first part of our experiment, that is standardizing our sodium thiosulfate solution that we have prepared over here. Now students, we move on to the first part of this experiment, where we are going to standardize a solution of sodium thiosulfate. We have already prepared a solution of sodium thiosulfate with a rough concentration of 0.018 moles per decimeters cube. So this concentration is not very accurate, so we need to standardize it with the use of another reaction. So students, to standardize this thiosulfate solution, we are going to react potassium iodate with potassium iodide in an acidic medium, and the iodine that is produced in this reaction is going to be standardized with the use of sodium thiosulfate, or more accurately, with the use of thiosulfate ions. So when you react iodate ions with I- ions or iodide ions in acidic medium, it turns into iodine and water. So one iodate ion would react with 5 iodide ions to form 3 I2 molecules, and this happens in an acidic medium. So this released I2 will dissolve in water, and we are going to titrate the I2 that is released with the use of our sodium thiosulfate or thiosulfate ion solution. So we have taken the sodium thiosulfate into the burette here. We have filled sodium thiosulfate all the way to the 0 line in this burette, and we have our potassium iodate solution with a concentration of 0.00167 moles per decimeters cube, 0.00167 moles per decimeters cube concentration. So we will be using this potassium iodate solution along with our potassium iodide solution that you have over here. We will take 10 milliliters of potassium iodate into a titration flask, and we add 1 cubic centimeters of potassium iodide along with 1 cubic centimeters of 50% sulfuric acid. Both of them are present in excess. The limiting factor would be the number of moles of potassium iodate in the reaction mixture, and this will regulate the amount of iodine that is produced. So I- ions and H plus ions are going to be in excess. However, iodate ions are going to be present in a limited number of moles, and this will regulate the amount of I2 that is going to be produced in this reaction. So we can calculate the I2 produced in this reaction, and the produced I2 is going to be reacted with sodium thiosulfate. So based on the volume of sodium thiosulfate spent, we can calculate the concentration of sodium thiosulfate. So students, without further ado, let's move on with the titration. We have a beaker labeled potassium iodate. We will take a small volume of potassium iodate into the beaker, and then we are going to use a graduated pipette along with the pipette filler to withdraw 10 cubic centimeters of potassium iodate into the pipette, and then we can transfer it into the titration flask. Now we have measured 10 cubic centimeters of potassium iodate, and we are going to transfer it into the titration flask. After doing so, we need to proceed to add sulfuric acid and potassium iodide into the reaction mixture. So we are going to measure 1 cubic centimeters of potassium iodide first. We can use a graduated pipette for that as well. We'll be using another clean graduated pipette, and we are going to measure exactly 1 cubic centimeters of potassium iodide here. Now students, we have measured 1 cubic centimeters of potassium iodide, and we will transfer it into the titration flask. And then, to acidify the medium, we are going to add sulfuric acid. We need to add 1 milliliter of sulfuric acid into the titration flask. So we have measured exactly 1 milliliter of sulfuric acid here, and we are going to add that into the titration flask. And as we add sulfuric acid to the titration flask, you would notice that the color of the solution will start to change. This is because in this reaction mixture in the titration flask, we have both iodate and iodide ions. However, the reaction between the iodate and the iodide ions will happen in acidic medium. And especially the iodide ion solution we introduced was highly alkaline. So when we add this sulfuric acid, which is really concentrated, so as soon as we add the sulfuric acid here, it will make the medium acidic, allowing the reaction to take place and produce iodine. And as iodine gets produced and dissolves in water, the solution turns brown. When iodine dissolves in water, the color of that solution is going to be brown. So we can observe that here. Now students, after adding the sulfuric acid, we are going to close the titration flask with the use of a petri dish or a watch glass, and then we have to keep it in the dark, and we are using a beaker that is darkened like so. So now the entire titration flask is going to be kept in the dark for the reaction to happen leisurely for about 5 to 10 minutes. We are going to keep the titration flask in the dark for 5 to 10 minutes until the reaction goes to completion. Afterwards, we are going to move on to the titration. Now students, we have allowed the reaction to take place in the dark for about 5 to 7 minutes. Now, I'm going to explain to you what we are going to do next. So in this titration flask in the solution, we have prepared iodine, and we would know the number of moles of iodine that will get produced in this reaction as we control the amount of iodate ions that we added into the medium. So we would know the number of moles of iodine that would get produced, and the produced number of iodine moles are going to be reacted with this sodium thiosulfate solution. So the concentration of the sodium thiosulfate solution we have taken into the burette is only roughly known. However, after the titration, based on the volume of sodium thiosulfate that is spent on carrying out this titration, we can calculate the sodium thiosulfate ion concentration in this solution. So as you add sodium thiosulfate, iodine molecules will react with sodium thiosulfate or thiosulfate ions to produce iodide ions and tetrathionate ions. So once more, I2 will react with S2O3 2 minus to produce I minus and S4O6 2 minus. One iodine will react with 2 thiosulfate ions to produce 2 iodides and 1 tetrathionate ion. So this way, the I2 in the medium will react with sodium thiosulfate, and as I2 concentration in the medium decreases, the brown coloration in the medium will decrease, and when the brown coloration turns to a slight yellow coloration due to the low concentration of iodine, at that point we will add the indicator. Indicator for such a reaction is going to be starch solution. So we will add starch solution, and as we add starch, you would notice that the color of iodine solution will turn into a blue-black color, and then from that point onwards, you are going to carry out the titration until the blue-black color completely disappears. Blue-black color will completely disappear when iodine in the medium completely reacts with thiosulfate to form I minus ions. So now let's go ahead and do that. We have our solution over here, and you can observe the color of the solution. It is a brown color. This is because we have iodine dissolved in this aqueous medium. And now we are going to start our titration. We can slowly start to add our thiosulfate ion solution or sodium thiosulfate. And as you can see, when we add sodium thiosulfate, the color of the solution gradually decrease. And when the color has decreased to produce a pale yellow color, at that point we will be adding starch solution. Now students, you can observe the color is starting to decrease. Earlier on it was a brown color, now the brown color has decreased slightly. We will continue to add thiosulfate into this medium. Now students, at this point you can see the color of the solution has turned to a light yellow color or a pale yellow color. At this point you can proceed to add the starch indicator. So we are going to add the starch indicator. We have our starch indicator here students. We will add a few drops of the starch indicator and see how the color changes when we add the starch indicator. You can see as soon as the starch indicator is added, solution turns a blue color, actually a blue-black color. You can add 2 drops. Now we are going to titrate this solution until the blue-black color completely disappears. You can see gradually the blue-black color is starting to disappear. There's a little bit more of a blue color still remaining. Hopefully the camera could capture it. There are fine blue color particles still in the medium, so this medium is not colorless yet. So when you are conducting the experiment, you'll be able to observe if the medium still has a slight hue of blue. In this case we do have a slight hue of blue, so we can adjust another drop and get to our end point. At this point students, the solution is completely colorless. So we have obtained our end point here. Now students, let's take a look at the burette reading. So the burette reading can be obtained by bringing the burette down so that you can observe the meniscus at your eye level. Over here we can see the burette reading is 6.7. The burette reading is 6.7. So after noting that down, we can repeat this experiment a few more times to observe whether we are getting to the same or similar concordant burette readings. Now students, we are going to repeat the same experiment one more time. We have our titration flask here and we have our potassium iodate solution here. We will be withdrawing 10 milliliters of potassium iodate using a graduated pipette like we did in the previous instance. Now students, we have measured 10 milliliters of our potassium iodate solution, and then we can transfer it into our titration flask. And then we are going to use another graduated pipette to withdraw 1 cubic centimeters of potassium iodide. So we have our potassium iodide solution here, and we will withdraw 1 cubic centimeter of potassium iodide. Now students, we have withdrawn 1 cubic centimeters of potassium iodide, and we are going to transfer that into our titration flask here. And then students, we are going to add our sulfuric acid. We need to add 1 cubic centimeters of 50% sulfuric acid. Now we have measured 1 cubic centimeters of 50% sulfuric acid, and we will be adding this into our titration flask. We'll mix the contents well, and as we did before, we will be covering it with a petri dish or a washed glass, and we'll be taking a beaker where we have covered the inside of the beaker with dark paper so that it creates a darker environment inside, and we are going to cover this titration flask with this beaker so that we allow the reaction to happen in the dark. So we will allow the reaction to happen for about 5 to 10 minutes in the dark, and then we will move on to our titration. Now students, we have allowed this reaction to go on for about 5 minutes in the dark. So let's titrate this with the use of our sodium thiosulfate solution. Keep in mind students, the initial reading is at 6.7. Initial reading is at 6.7. So we are going to start the titration with the initial reading of 6.7, and we need to notice the final reading and then obtain the difference to calculate the amount of sodium thiosulfate spent on this titration. So at this point students, you can observe that the color of the solution has decreased significantly. So at this point we can add our starch indicator. So we are adding a few drops of starch. You can see the color of the solution changes to a blue-black color. Now after adding the starch indicator, we can continue to titrate this solution until a colorless solution is obtained. So it's a lighter blue color now. We are close to the end point. We still have some blue coloration in the medium. We can add a few more drops. Now students, the medium is completely clear. There is no blue coloration observed. So now students, we are done with the titration. So as you can see, this is a clear solution. So let's take a look at the Buret reading now. So Buret reading is above our eye level. We'll bring it down to our eye level here. So the Buret reading is 13.6. So the initial reading was 6.7. The final reading here is 13.6. So the difference between the two is 6.9. The difference between the two is 6.9. So initial Buret reading is 6.7. Final Buret reading is 13.6. Difference is 6.9. So if you remember our previous titration, in the first titration, the amount of sodium thiosulfate that was spent was 6.7. In the second titration, the amount of sodium thiosulfate spent was 6.9. So now let's move on to the third titration. Now we are moving on to the third titration. So we have our titration flask here. Like we did in the previous two instances, we will measure 10 milliliters of our potassium iodate solution. So we are going to measure 10 milliliters of the potassium iodate solution here. Now students, we have measured exactly 10 milliliters of potassium iodate, and we are going to transfer it into our titration flask. And afterwards, we can move on to adding 1 milliliter of potassium iodide. We will be using a different graduated pipette here, and we are going to withdraw 1 milliliter of potassium iodide using a different graduated pipette. As you can see, we have measured exactly 1 milliliter of the solution, and we are transferring it into our titration flask. And afterwards, we will measure 1 milliliter of 50% sulfuric acid, now we have measured 1 milliliter of 50% sulfuric acid, and then we are going to transfer it into our titration flask, and we are going to cover it with this petri dish. After mixing the contents well and covering the titration flask with a petri dish, we can now keep the titration flask in the dark using this beaker, and we'll allow this reaction to take place for about 5 to 10 minutes, and then we'll proceed to our titration. Now we are going to move on to the third titration. We have allowed this reaction to take place over a period of 5 minutes. So now let's proceed to the titration. Keep in mind, students, the initial volume or burette reading that we are starting with is 13.6. That was the final burette reading of the second titration. When it comes to the third titration, it will become our initial burette reading. So then we will proceed with our titration. You can see the color of the solution is quite dark. However, after a while I will show you how the color of the solution decreases when we keep on adding sodium thiosulfate. Now you can observe how the color has decreased significantly. Now students, at this point we can add our starch indicator. You can see the solution turning blue-black in color. Then we will titrate this until the solution becomes colorless. The blue color gradually decreases as we keep on adding sodium thiosulfate, and eventually it will be colorless. We have obtained our endpoint. So the solution is clear now. This means we have obtained our endpoint, and it is time for us to read the burette reading. So the burette reading is 20.4. The burette reading is 20.4. So let's take a look at the 3 titer volumes that we obtained for the 3 titrations. For the first titration, the volume was 6.7, then 6.9, and then 6.8. So after noting these volumes down, we can calculate the concentration of sodium thiosulfate in our whiteboard sessions. So for the time being, we can move on to the next part of our experiment, where we will be trying to determine the dissolved oxygen content of a water sample that we have here in the lab. Now students, in this part of our experiment, we are going to focus on collecting a sample of water and then treating it with Mn2 plus ion solutions and iodide ion solutions. So in this second step, we are going to use these reagent bottles to collect a water sample, and then we are going to add our MnCl2 solution to it. As 1 cubic centimeter of MnCl2 solution will be added to this, and then it will be added with Ki or potassium iodide solution as well. So let's observe how we collect a water sample. You will first remove the stopper of the reagent bottle. Make sure the reagent bottle is clean. You will take a small volume of the water sample into the reagent bottle, and you can wash or rinse the reagent bottle using that water sample. After rinsing it once, you can remove the water, and then you can repeat this a second time as well. We will rinse the water bottle twice like this with the water sample you are going to be taking into the reagent bottle. Now students, we have rinsed this reagent bottle with the water sample that we are going to take into this reagent bottle. So over here we have our well water sample that we showed earlier. So we are going to determine the dissolved oxygen level of this well water sample, and when you are collecting the water into this reagent bottle to be analyzed, you have to dip the reagent bottle into the water sample at a 45-degree angle and allow the water to flow into the reagent bottle without causing any bubbles to form. So we will carefully do that now. So now we have collected the water sample into the reagent bottle without any bubbles in it, and then we will close or place a stopper of the reagent bottle while the reagent bottle is submerged in water, like so. And when you take the reagent bottle out of the water, it should not have any air bubbles in it. You can see even when you turn it upside down, there are no air bubbles trapped in it. So this is how you would be collecting a water sample into a reagent bottle. Now let's keep it aside. Now students, you observed how we filled this reagent bottle with our well water sample. So this entire reagent bottle is filled without any air bubbles in it with well water sample. So now to the second reagent bottle, we are going to be filling tap water. So let's move on to that part now. Now we move on to collecting a tap water sample. So we have taken a sample of tap water here into this container, and we have another reagent bottle that is now empty, and we have labeled our well water sample that we took into this reagent bottle, so you can see that here very clearly. So to this second reagent bottle, we are going to fill tap water. So we will first wash this reagent bottle like we did in the previous case. We'll take a little bit of water, and then we will rinse the reagent bottle like so. And we will repeat that process one more time. So after rinsing this bottle with tap water twice, we can now proceed to fill this reagent bottle with tap water. So like we did in the previous case, we will keep this reagent bottle at a 45-degree angle and then slowly submerge the bottle in water, and you can see the water is starting to flow into the reagent bottle, and you need to eliminate any air bubbles that are there inside the bottle. And after making sure there are no air bubbles, you can place the stopper as well. Make sure that there are no air bubbles trapped in the stopper as well, because in most cases you will see reagent bottles with hollow stoppers. So this stopper, you can see it is hollow. So make sure there are no air bubbles trapped in the stopper as well, and then you can place the stopper inside water like so, and then we can take the reagent bottle out. This way we do not observe any air bubbles here. If you turn it upside down, you can see that there are no air bubbles trapped in this reagent bottle. So now we will move on to the next step of this process. Now students, we have over here two reagent bottles, one filled with tap water and the other filled with well water. So we are going to analyze the dissolved oxygen levels of both of these water samples. So now the next step would be to add 1 cubic centimeter of manganese dichloride into each of these reagent bottles, and then we are going to add 1 cubic centimeter of potassium iodide as well. When you add manganese dichloride or manganese 2 chloride, it introduces Mn2 plus ions into the medium. We have a highly concentrated Mn2 plus ion solution here. You can see the manganese dichloride solution has a concentration of 3 moles per decimeters cube. So we will include 1 cubic centimeters of that solution into each of these reagent bottles. So that will introduce a sufficient amount of Mn2 plus ions into the medium. And then we are adding potassium iodide. If you can remember, potassium iodide solution was made by dissolving the relevant mass of potassium iodide in 8 moles per decimeters cube concentrated sodium hydroxide solution. So this contains enough and more potassium iodide as well as sodium hydroxide. So when we have both of these ions in the medium, both of these ions meaning Mn2 plus ions and hydroxide ions in the medium, they will react to form manganese hydroxide. However, students, this is not going to stay as MnOH2 for too long because manganese hydroxide is going to react with the oxygen that is present in the water sample. So whatever the dissolved oxygen will react with MnOH twice, and this produces MnO2, manganese oxide. So manganese oxide is a brown color present, students. You will see a color change happening as Mn or manganese hydroxide gets oxidized to manganese oxide. So if you go through what is happening one more time, we will add 1 milliliter of Mn2 plus ion solution, and then we will add 1 milliliter of potassium iodide solution. Potassium iodide solution is made by dissolving potassium iodide in highly concentrated sodium hydroxide. So therefore, it will bring hydroxide ions into the medium as well. Mn2 plus ions and hydroxide ions will form manganese hydroxide, and manganese hydroxide in the presence of oxygen that is dissolved in this water will turn into MnO2. So all of the oxygen in this water sample will be used to convert Mn or manganese hydroxide into manganese oxide. Since excess amount of manganese hydroxide is present in the medium, the limiting factor for this oxidation is going to be oxygen dissolved in water. So based on the amount of oxygen dissolved in water, certain amount of manganese hydroxide will be converted into manganese oxide. So afterwards, students, you will notice when we add potassium iodide, there were iodide ions introduced into the medium. So later on, at a later step, right before the titration, we are adding sulfuric acid. In the presence of an acidic medium, I- ions and the MnO2 that was formed in this solution is going to react together to form iodine and Mn2+. And the liberated iodine or iodine that is produced here can be titrated against the sodium thiosulfate ion solution that we standardized in the previous step. So this is the process that we are going to use to determine the oxygen content found in this water sample. So let's move ahead and do that. The first thing that we need to do is we need to add a small volume of Mn2+ ion solution. So we have manganese dichloride here, and we will be adding a small volume of manganese dichloride into the first sample. So we have manganese dichloride sample here. Let's first withdraw 1 cubic centimeter of manganese dichloride into this graduated pipette. We are going to withdraw just 1 cubic centimeters all the way up to this mark over here. Now we have taken exactly 1 cubic centimeter of Mn2+ solution, and when you're adding Mn2+ solution into this reagent bottle, the tip of the pipette should be inside the water surface, not over the water surface. So you have to make sure to insert the tip of the pipette into the water sample here. At this point, some water might overflow, and that is expected. It is not going to be a problem, as we expected certain amount of water did overflow, and it is going to be expected. So now, students, we have introduced 1 cubic centimeter of manganese hydroxide into this tap water sample. We will do the same for the other sample as well. Now we move on to our well water sample, and we are going to measure 1 cubic centimeter of our Mn2+ aqueous solution. So we have taken 1 cubic centimeter of Mn2+ or manganese dichloride solution, and we will open the lid and place the tip of the pipette inside the water, and then we will release the Mn2+ aqueous solution into the water sample. As expected, there will be a certain amount of water that is going to overflow, and that is expected when you are carrying this experiment. So students, after adding Mn2+ to each of these water samples, now it is time for us to add our alkaline potassium iodide solution. So we have our alkaline potassium iodide solution here. So we have our potassium iodide solution here, and keep in mind this is an alkaline potassium iodide solution, meaning the potassium iodide solid was dissolved in 8 moles per decimeters cube concentrated sodium hydroxide solution. So This is an alkaline potassium iodide solution. This contains both potassium ions, iodide ions, sodium 1 plus ions, and hydroxide ions. And then we are going to use another graduated pipette and take 1 cubic centimeter of this potassium iodide solution. Now students, we have taken exactly 1 cubic centimeter of this potassium iodide solution, and we are going to insert the tip of this pipette when we are adding our potassium iodide solution into this. And as you can see, when we added the potassium iodide solution into this water sample, the entire water sample started turning into a brown color. Now this is because it forms manganese hydroxide, and then the produced manganese hydroxide reacts with oxygen and forms MnO2, manganese oxide. And manganese oxide is brown in color. Manganese hydroxide, on the other hand, is a white color substance. But manganese oxide is going to be brown in color. You can see when we added potassium iodide dissolved in sodium hydroxide into this water sample, we observe the formation of manganese oxide. Now students, let's go over what happened in this reaction one more time. We initially introduced Mn2 plus ions into the water sample through manganese dichloride, and then we added potassium iodide solution. Potassium iodide solution had sodium hydroxide as well in it. So as sodium hydroxide and potassium iodide enters the medium, the OH minus ions together with Mn2 plus ions will form manganese hydroxide. Manganese hydroxide will react with the oxygen in the water sample and will get oxidized to form MnO2. And MnO2 is a brown color precipitate, which you can see in this reagent bottle. There's a solid that has formed here, and that is going to be your manganese dioxide or manganese 4 oxide. So students, we have now formed our manganese dioxide precipitate. Here, when the reaction was happening between manganese hydroxide and oxygen, all of the oxygen in the water sample is used up to produce manganese dioxide and water. So based on the amount of manganese dioxide that is produced, we can determine the amount of oxygen that was dissolved in this water sample. So we have observed what we should do to one water sample before we move on to a titration. So let's keep that water sample aside, and we can now move on to the second sample of water, where we have well water taken into our reagent bottle. So we have a well water here, and we have already added Mn2 plus aqueous ion solution, and it's now time for us to add 1 cubic centimeter of potassium iodide solution or alkaline potassium iodide solution. We have taken 1 cubic centimeter of potassium iodide solution. Now we can add this potassium iodide solution into this water sample by inserting the tip of the pipette into the water sample. As you can see, as potassium iodide enters the water sample, the reaction I mentioned earlier would take place, producing MnO2. So first, a white color precipitate will be formed, manganese hydroxide, but we will not observe this very clearly. But this manganese hydroxide will react with oxygen to form MnO2, which is going to be a brown color precipitate. So that brown color precipitate is very prominently seen here as manganese hydroxide oxidizes using up the oxygen that is dissolved in water. It produces manganese hydroxide. You can see after we leave it for a while how the two different water samples appear for the time being. So over here we can see the formation of manganese dioxide very clearly, and over here we can see the reaction is still happening. So we will allow this reaction to take place for a while, and then we will move on to the titration. Now we can observe the differences of these two samples. We can see the color of the precipitate that is formed in the tap water sample and the color of the precipitate that is formed in the well water sample are two different colors. So I told you manganese hydroxide is also a water insoluble white color precipitate, but it will react with the oxygen in the water sample. Here there is no other oxygen, only the oxygen in the water sample is available. So manganese hydroxide, the white color precipitate that is formed within this water sample, will react with the oxygen in the water sample and turn into manganese dioxide. So manganese dioxide is going to be a brown color precipitate. So this water sample is a much darker brown than the well water sample at this moment. This is because the manganese dioxide precipitate has gotten formed here in a higher quantity than in the well water sample. This indicates, even visually, you can make a small assumption that the oxygen content in the tap water sample is slightly higher than the oxygen content in the well water sample. And in the well water sample, you might observe that there is a slight white color nature to the upper part of this precipitate. So this is because some of the precipitate still remains as manganese hydroxide. If sufficient amount of oxygen was there in this well water sample, that manganese hydroxide would have also gotten converted into manganese oxide. So now it is time for the titration. So right before the titration, we are going to add 1 cubic centimeters of our 50% sulfuric acid. So we have our 50% sulfuric acid here, and we have a fresh pipette here, and we are going to draw 1 cubic centimeters of sulfuric acid into the pipette, and then we are going to add it to our tap water sample. Now, after adding sulfuric acid into the tap water sample, you can observe that the precipitate is starting to dissolve. Now you have to invert this reagent bottle a few times to ensure the proper mixing of sulfuric acid with this solution. And as you mix, you can see almost all of the precipitate dissolves and solution turns into, or the brown color suspension we had earlier now turns into a brown color solution. Now this is completely a brown color solution. We will keep the well water sample aside for the time being, and we'll focus on the tap water sample. So what were the observations? The brown color precipitate dissolved upon addition of sulfuric acid and produced a brown color solution. Brown color precipitate dissolved to form a brown color solution. So what is happening in this reagent bottle here? As you add sulfuric acid, the medium becomes acidic. And in this reagent bottle, earlier on we have added potassium iodide. So iodide ions were present in the medium. And in the presence of an acidic medium, iodide ions and manganese dioxide will react to form Mn2 plus, manganese 2 plus ions, iodine and water. So the I minus ions that were present in the medium got converted into iodine, or I minus ions got oxidized into iodine in the presence of H plus or in the presence of an acidic medium, while manganese dioxide got reduced to form Mn2 plus. So the iodine that is produced, as you know, when iodine dissolves in water, it is going to appear brown in color. So the appearance that you see over here, the brown color appearance in the solution, is there due to iodine being dissolved in water. So now we are going to take 100 cubic centimeters of this solution and we are going to titrate that 100 cubic centimeter aliquot of this solution with our sodium thiosulfate solution that we standardized earlier. Now students, we have a 100 milliliter measuring cylinder here and we are going to take 100 milliliters of this solution into our measuring cylinder and then we will transfer it to our titration flask. Now we have measured exactly 100 milliliters of this solution and we will transfer 100 milliliters of the solution into our titration flask. And you can observe the color of the solution. And then we will titrate this solution that is in the titration flask with our standardized sodium thiosulfate solution. So we have filled this burette with that standardized sodium thiosulfate solution all the way to the zero line. So we can now start our titration. Just like we did in the previous titration, we are going to add sodium thiosulfate until the color of the solution decreases to a pale yellow color. After that, we will add our starch indicator that we have over here, and then we'll continue on with the titration until the blue-black color that we observe after adding the starch indicator completely disappears. So let's start the addition of sodium thiosulfate. Now students, you can see the color of the solution has decreased quite a bit. It is no longer a darker orange color. Now you can see the two colors are not the same anymore. This would indicate some of the iodine present in the aqueous medium has reacted. So now would be a good time to add our starch indicator. So we are going to add a few drops of starch indicator, and you can see as we add starch, the solution changes color. Now it is a dark blue black color. You can observe the color very clearly here. And now we have to titrate this solution until all of this blue color completely disappears. We still have a slight blue color. We can add a few more drops. And now the blue color has completely disappeared. You can observe the solution is no longer showing any blue color, so we have obtained our end point. So we obtained our end point at a burette reading. We will need to bring the burette to our eye level or meniscus to our eye level to read this burette reading. So the burette reading is 5.2. The burette reading is 5.2 cubic centimeters. After noting it down, we can move on to the next titration. Now, students, we are going to repeat the same titration we did earlier so that we will have two readings to work with. So we are going to take our titration flask and the measuring cylinder, and we will be measuring 100 milliliters of the solution that we have in this reagent bottle. We have measured 100 milliliters of the solution into the reagent bottle, and now we are going to transfer it into our titration flask. Now you can observe, students, the color of the solution. Color of the solution is a bit of a brown color or light brown color, and we are going to add our sodium thiosulfate solution into this and carry out the titration. So sodium thiosulfate ions or thiosulfate ions will react with iodine, and iodine will be reduced to form iodide ions, while our thiosulfate ions will oxidize to form tetrathionate ions. So now we are going to start the titration, and the initial burette reading is 5.2. The initial burette reading is 5.2. While keeping that in mind, we can start our titration. You can see that at this point the color of the solution has significantly decreased. So we'll continue to add a little bit more sodium thiosulfate, and when it is a pale yellow color, we will start adding our starch indicator. Now you can see at this point the solution has turned into a pale yellow color. So at that point we can add our starch indicator. You can see the color changing to a blue color. So with iodine, starch will form a blue-black color, and we are going to titrate until this blue-black color completely disappears. Now we have a lighter blue-black color. We are going to add a few more drops of thiosulfate ion solution. We need one more drop. There is still a very slight blue color over here in the medium. So one drop actually clears this blue color. You can observe that the solution is now colorless. So we have titrated our solution until all of the iodine molecules in the solution completely gets titrated with sodium thiosulfate. So over here we have our colorless solution. Now it is time for us to take a look at the burette reading. So again, the burette reading is above our eye level. So now the burette reading can be read easily. The burette reading is 10.5. The burette reading is 10.5. So the initial burette reading was 5.2 and the final burette reading is 10.5. The difference between the two is going to be 5.3. So for the second titration, our titer volume is going to be 5.3. For the first titration, the sodium thiosulfate volume we used was 5.2. For the second titration, it was 5.3. So let's note these details down and move on to the second water sample we have, which is the well water sample. Now let's move on to the second titration. Here we have our well water sample, and we can observe that it has formed a precipitate here, and we are going to open the stopper of this well water sample reagent bottle, and we are going to add just 1 cubic centimeter of 50% sulfuric acid. So we will use our pipette and we will withdraw 1 cubic centimeters of 50% sulfuric acid. Now we have taken 50% sulfuric acid into our graduated pipette. Now we are going to add it to our well water sample. After that, students, we are going to turn it upside down a couple of times and mix it really well. And as you can see, all of the precipitate completely dissolved, producing this pale brown color or orange color solution. So this is due to iodine dissolving in water. Now we are going to measure 100 milliliters of this solution and take it into our titration flask here and proceed with the titration as we did in the previous instance. We have measured exactly 100 cubic centimeters of solution here, and now we will transfer it to this titration flask. And afterwards, students, we will start our titration. So we have in this burette our standardized sodium thiosulfate solution, and we have filled it all the way up to the 0 line. So now let's start adding our sodium thiosulfate solution little by little until we observe a pale yellow color. You can see we have already obtained a slight pale yellow color in the titration flask with the addition of a few milliliters of our sodium thiosulfate solution. And then at this point we can proceed to add our starch solution. We will mix it well. So we have a blue-black color present in the medium now, and we are starting titration, and we are carrying out the titration until this blue-black color completely disappears. We have obtained a very pale blue color here. Now we have to add sodium thiosulfate a bit more slowly. And at this point, students, we have obtained our end point. So we can move on to taking the reading at the end point, but before we do, we can observe the color of the solution. So the solution is now completely colorless. Now let's move on to taking the reading. We can bring the meniscus to our eye level. So the reading is exactly 2.4. The reading is 2.4. So for the first titration, we spent 2.4 cubic centimeters of sodium thiosulfate solution. Let's move on to the second titration. Now students, let's move on to the last titration. We have our measuring cylinder here, and we will measure exactly 100 milliliters of the solution using the measuring cylinder. We have measured 100 milliliters of solution here, and now we are going to transfer this into our titration flask. And we can move on to titrating this against our sodium thiosulfate solution. So students, keep in mind we are using the same sodium thiosulfate solution in the same burette. So the initial reading over here after the first titration is going to be 2.4. So for the second titration, the initial reading is 2.4. So after noting that down, we can move on to our titration. Now, the color of the solution has significantly decreased. So at this point, we can proceed to add our starch indicator. And you can observe the blue-black color upon addition of the starch indicator. And now we are adding sodium thiosulfate until the blue-black color completely disappears. So with just one more drop, the blue-black color will completely disappear. Just slight, yes, now the color of the solution is colorless. Actually, the blue color of the solution is completely gone now. We have obtained our endpoint. So now we can read the burette reading at our endpoint. Burette reading at the endpoint is 4.9. Burette reading is 4.9. Now students, after noting down the volumes here, we can move on to the summary of this experiment. In the beginning, we observed how we are going to standardize a sodium thiosulfate solution, and then we observed how to collect a water sample from a water body. As soon as we collected the water sample, we added Mn2 plus ion solution into the water sample, followed by an alkaline potassium iodide solution. At this point, manganese hydroxide was formed, and the manganese hydroxide reacted with the oxygen in the water sample to produce manganese dioxide, and the manganese dioxide is going to appear as a brown color precipitate. And after acidifying this sample of water, when you add H plus by acidifying the sample, the iodide ions in the medium will react with MnO2 to produce Mn2 plus and iodine, and the produced iodine make the solution a pale brown color. And then we titrate the iodine produced in the solution with our standardized sodium thiosulfate solution. So this leads to calculating the oxygen content present in water. Now it is time for us to take down the details about the different types of titer volumes we observed into the classroom, and we are going to calculate first the concentration of the standard sodium thiosulfate solution we prepared, and then we are going to calculate the dissolved oxygen content in each of these two water samples. Now students, this is the last of the practicals we have in our lab